Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders, year 2019, problem number 3. Let G consists of x1, x2 up to xn be a group. These elements form a group, enumerated in any way. Let A be a matrix where A, ij equals 0 if xi xj inverse equals xj xi inverse, and it's 1 otherwise, for I and j from 1 to n. We wish to find the parity of this determinant. The parity, not the exact value, because it's rather possible to do, but just the parity. And also notice that, as it is often the case in differential geometry, I denote entries of the matrix. The index of row is in the upper index, and the index of column is in the lower index. It does not mean that we raise our matrix to the power of I, it's just the indexing of our matrix. Alright, so here are my hints for this problem. First, show that when we take one row of our matrix and we sum it, so we are changing the number of columns, but I stays the same, this number is first even, and second does not depend on I. It's even and does not depend on I. And now, crucial fact, view this matrix A as a matrix over the field Z2. So it's the simplest field. It has two elements, 0 and 1. Well, it's just, modulo 2, arithmetic modulo 2. And show that this vector, which has entries 1, 1, and so on, is in the kernel of our matrix. And since our matrix has some vector, non-zero vector which goes to 0, it cannot be invertible in this set of matrices over field Z2. And this should be enough. So give this problem a try, and I will see you in just a minute. Alright, so let's take a look. Let's investigate the sum. J goes from 1 to n. I, A, J. Alright. Now I will introduce a handy notation, Iversonian bracket. I will write we are summing of terms of this form. So if you don't know how this bracket works, notice that in this bracket we have some formula, and this bracket is evaluated to 1 if this formula is true, and it's evaluated to 0 if it is false. Alright, now, first thing, notice that we are summing just over, well, all elements of our group. So we can write that it's sum, if we take sum over all elements x of our group. Okay, let's write it in yellow. So xi times x inverse different than xi inverse. Alright. Now I will do a clever change of variable. Instead of x, I will put, let x be equal xi times y, where I is fixed. And then notice that our sum, we can now just sum over all elements y of our group, because notice that this function is really a bijection. So there is only one y corresponding to any x, and any x, just one x corresponding to any y. So we can just sum in different order. And now notice that if I do it, I have xi, and well, instead of x, I can put xi times y, xi times y. No, sorry. Is it right? Yes, it is. Yes, it is. All right. Different than, and here I have, no, sorry, you know what? No. Let's do it in different order. Sorry about that. Let's put x to be y, xi. But still, the same is true, which I said. And here I have y, xi, xi inverse. All right? So we are summing over all y in our group. And notice that now, well, we know that I will use this fact basically, that AB inverse is the same as B inverse A inverse, general fact about any group. So it's xi inverse times y inverse, different than y xi inverse. Now we can do simplifications, because notice, also let's write y in green to be consistent. Because now notice that now this cancels, and we have y inverse is not equal y. And also we can express it, and also let's write it in green. And we can multiply this condition by y, and we have the following. We are summing over all elements y. Y squared is different than the identity of our group. All right. Now, clearly, we see that this sum does not depend on y, on I. It disappeared along the way. So this does not depend on I. All right, but moreover, second observation, I claim that this number is even. I claim that it is even. How do I know that? Well, notice, let's investigate the nature of this set. So let, for example, S be equal to all elements y of our group, which are not such that y squared is not of the identity. Notice that all these numbers can be paired, because when we have a number, because this just means y squared is not equal 1, that any element of this set, its inverse, it's not the inverse of itself. So notice that A belongs to S if and only if there is B in our group such that B is not equal A and AB equals 1 equals BA. So notice that these numbers A and B can be paired. We can take A from this set and B from this set, and they are different. So, and every number can be paired with its inverse, which proves that this is even, since we can pair A with its inverse A inverse, where A is not equal to its inverse. So I have justified that the sum of any row stays the same as and is even, which leads to a very important observation. So now, from now on, let's view our matrix A as n by n matrix with entries from Z2 field. And notice that then we have the following. What happens when I take matrix A and I multiply it by column vector of just ones. Well, I have now vector of sums of what? Well, sums of columns. So I goes from 1 to n. What? Let's write it like that. J goes from 1, n, I, j, and so on. And also here should be 1 because it's first entry, and so on. Alright, and we have justified that all these numbers are the same and are even. So we are dealing with the 2 field, so all of them are zeros. All of them are zeros. Which means, because in Z2 field, any even integer is viewed as 0, any odd integer is viewed as 1. Which means, notice that 1, 1, and so on is in the kernel of our matrix. In its null space, if you wish. So it means that this function, viewed as a linear function taking z2 to the power of n and returning other vector, this function is not invertible. It's not invertible because it's a square matrix and it's not injective. Alright, which of course means that the determinant of this matrix, let me be very clear, determinant again viewed as element of Z2 must be 0. Which means, of course, that the determinant of our matrix is even. So the determinant of A is even. Because in Z2 it's 0. And this closes our problem. Our determinant is even. A very beautiful problem. So, by the way, very often when dealing with matrices with zeros and ones, it's a good idea to view it as a member of the ring of matrices with coefficients from field Z2 and to do some manipulations. In our problem, it was crucial to observe two things. First, that any sum over any sum of any row stays the same and is even. It was the crucial observation. And also, notice how handy the Iverson bracket can be. All of these manipulations were purely logical, and it went from this to this. I highly recommend. This Iverson bracket is not completely standard, unfortunately, but it is very handy, very, very handy. You can read more about it. It was proposed by the authors of Concrete Mathematics. They strongly advocated it, and I do as well. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.